In this video, I'm going to walk you through the tissue linear regression example that's found in the Vdi library. I'd like to first quickly show you how to download the Vdi libraries. So to do that, you go to your favorite browser and you can type into the address bar just vdisoftware.net, and this should redirect you to my website and to the specific tab that has to do with software, where you'll immediately be able to go to the Vdi download page, which is really just a Google Drive. So you click on this here, this Vdi Google Drive repository, and you can use this. You'll basically see all of the available versions, and you can use this to download the most recent one. In this case, this is Vdi 1.1, which was released March 2nd, 2021. Once you download this library, what you do is, this is really just a zip file. You unzip it, and then you go to your MATLAB installation. So I have it set up here, and you basically go to the directory where you've unzipped it, which will be called Vdi. You right-click it. In this case, this is on the path, but if it's not on the path, you simply select the option here. It would read Add to Path, and then you would select selected folders and subfolders. And that would be it. This is the entire installation process. I have the example open here on the left, and if you want to open it yourself to follow along, you can go to the Vdi installation directory, go to the examples subdirectory, and then open up this file over here, example image analysis 5 tissue linear regression. So if you double click it, you'll get this script that you see here. I'm going to quickly walk you through the lines, and then we're going to run it, look at the output, and then I'll give you some advanced usage tips in using maybe the library and tailoring it to your needs. So let's start by looking at the script. This is not a long script. If I scroll all the way down, you see it's only 125 lines, and probably half of them are comments to help you understand what's going on. Now, the first part of the script, that is this selection over here, has to do with loading the data that you need to run the script. Now, for example, this first line over here loads the T1 anatomical MP-RAGE image. Now, this image is already, the data itself can be found in this example data subdirectory. So if I open this up, you can see that there's an MP-RAGE anatomy.nii file here, and this is what this line does. .nii files are nifty files, and these are a popular format for storing neuroimaging data. It's used, for example, by FSL and many other packages. This nifty image is loaded using the Vdi.io class. Vdi.io stands for input-output, and this class, Vdi.io, handles the loading and saving of different types of datasets. It has a command called load.nii, which loads nifty files. And this command over here, vdio.load.nii, and then the file name, loads the nifty data and returns a variable that contains the nifty data. Now, this variable over here is of a particular and special type called a Vdi Image Object. And it really contains not just the image data in each pixel, but also all of the metadata that explains how this data is oriented in 3D space in the scanner relative to the patient. And this is, of course, very important if you want to overlay different types of data sets one on top of the other. Now, let me just run this line over here. I can do this by highlighting it, and on Windows, all I have to do is I have to right-click, and then I can select Evaluate Selection. So this will just run the line I've highlighted. And this variable over here, image MPR, contains this image data. If I type in image MPR, the command line, you'll get this complex looking variable that really contains all of the image data and metadata. Now, looking at it this way is not very constructive. It's kind of hard to understand what the different fields mean, but you can look at it interactively by typing in VDI Image Browser and then telling it, I'm going to give you a VDI image, and it's going to be image MPR. So if I type this, this will bring up the interactive browser, and you can see that I actually see here this MPRH dataset. And I can go through it, different planes, and look at the data that I've loaded. We'll come back to this in a moment. I'm going to close it now and get back to the script. The next 3 lines load the white matter, gray matter, and CSF segmented maps. Now these maps have been segmented from the MPRH anatomical map, and I've used SPM12 to segment them. There are many software packages that will do this. SPM, FSL, FreeSurfer, and AFNI, and others. And you can select your weapon of choice. The important thing to do is to make sure that your nifty images are normalized between 0 and 1, the white matter, gray matter, and CSF images. Now they can be binary or probabilistic. It doesn't really matter, but they have to sum up to 1. Now, it just so happens that SPM, when it segments the white matter, gray matter, and CSF, it returns images that are scaled between 0 and 255. This has to do with using 8 bits to store the data. So these images, this, for example, image white matter variable, or image gray matter, or image CSF, vary between 0 and 255. These are really probabilistic maps that kind of tell us how much SPM thinks each voxel is CSF, gray matter, and white matter. If I sum all of them up, I should get 255. To normalize them from 0 to 255 to 0 to 1, I have to divide them by 255, and I do this with these 3 lines over here. Now, one of the nice things about these VDI image objects is that they kind of behave like just arrays of numbers. So despite the fact that image white matter, image WM, is a complex VDI image object, I can still write this simple looking command, image white matter equals image white matter divided by 255, and it will divide each voxel in the image by 255 and normalize the image. Same for gray matter and CSF. Finally, for display purposes, I can set the display limits of each of these tissue maps to between 0 and 1. This will only make a difference if you look at these images using VDI Image Browser. So what I'm going to do is I'm going to highlight all of these lines. I'm going to run them. Okay? When you come to analyze your data, what you should do is you should write a routine in your preferred language of choice, MATLAB, Python, whatever, that takes your neuroimaging metabolic data and saves it in a format like Nifty that can then be shared by either used by VDI or even other software libraries out there like FSL and others. So I'm going to assume that you have a way of doing this with your data. Now, the next thing, or the next part of the script, calculates the gray matter, white matter, and CSF fractions within each of the spectroscopic voxels defined by image NAA. And this is done with a simple command called calculate fractions. And really what happens here, you have these 3 commands which do this for each of the tissue fractions. So let's look at one of them. Let's look at this command over here, which does it for the white matter tissue mask. So this is actually a method in the image white matter object, meaning that when you run the calculate fractions command called from image WM, it will use the data in this image WM object, in the white matter tissue mask. And it will downsample it, basically, to the grid defined by the spectroscopic image NAA. So the end result of this will be frac Wm, the fraction of white matters in each of the spectroscopic voxels. And the same happens for gray matter and CSF. Now, if this sounded a bit complicated, don't worry, let me just highlight these. I'm going to right-click and evaluate this selection. Calculating the fractions might take a few seconds, depending on how powerful your computer is. But now I have these, all of these images, the fractions of CSF, gray matter, and white matter, inside each of these spectroscopic imaging voxels in this NAA dataset. This actually has nothing to do with the values of NAA in each voxel. It just needs the geometry of your MRSI grid. Now, I'm going to call again Vdi Image Browser. I'm going to feed it this Vdi Image Object, and I'm going to, let's put in all of the things that we've had so far. Let's put in the anatomical image, the gray matter, CSF, and white matter tissue masks, the NAA image, and then the fraction images. Remember, these are just images. Just images telling you what's the fraction of, for example, this tells you what the fraction of cerebrospinal fluid is in each MRSI voxel. But this is just an image, really. So I'm going to run this. And you can see, first of all, here's your anatomical image. This is a white matter image, gray matter, CSF. And here's the 2D NAA slice. Now, you see that it's in a lower resolution compared to the higher resolution MP-RAGE image. And if I look at the frac WM, frac gray M, GM, and frac CSF images, which are here, I'm going to see that downsampled white matter, gray matter, and CSF images downsampled onto the grid of the NAA MRSI. So again, this dataset over here, which is frac WM, simply tells you how much white matter there is in each of the coarse MRSI voxels in the NAA dataset. Now, I'm going to close this, and I'm going to move on to the next part of this tutorial video, which runs the linear regression. Now, the entire really heart of this, the linear regression part, is done with a single line. This again has to do with the sort of flexibility of the Vdi image class in handling complex operations. This is what's called operator overloading in object-oriented programming, basically meaning that you can manipulate these complex Vdi image objects, image NAA, frac GM, and frac WM, using the same operators as you would in manipulating matrices in MATLAB. And what this does, when I run this, it will solve a set of linear equations, these results, onto the command line. So if I evaluate selection, it will tell me what the basically estimates are. And finally, the last part here just visualizes these results. So we're going to run this part without going through the different commands, and then we're going to look at the resulting figure. So let me just run this entire section. And I get this nice looking figure, and let me walk you through the 4 panels. This panel over here, these are just 2 histograms telling you what the fraction of white and gray matter is in each of the spectroscopic MRSI voxels. So you can see that there are more voxels with a lot of gray matter compared to more voxels with a lot of white matter. And it's just, again, a sanity check to see that what your data looks like, that these histograms don't look too weird, or that they sort of agree with what you see visually. Where, for example, when you look at the Vdi Image Browser downsampled images on your screen. What you see here is the NAA signal from your 2D slice plotted as a function of the white matter fraction and the gray matter fraction. So each dot here represents a different MRSI voxel. So the z-axis is the NAA signal, and basically each dot here is an MRSI voxel. So for example, this dot over here is some voxel that had a low amount of gray matter, relatively speaking, and a low amount of white matter, meaning that it probably had a fair bit of cerebrospinal fluid. Most of the voxels fall on this diagonal over here, and if I tilt this image, you can see it. And this is because most of the voxels have very little CSF, so the sum of white matter and gray matter should be 1. And you can see that, for example, these elements on the diagonal, this element over here has a lot of white matter and a little bit of gray matter. This element over here is all white matter and no gray matter. And the elements over here have a lot of gray matter and no white matter. And all of this diagonal really has no CSF. The plane through this is the result of the linear regression to the data. So the results of fitting the data using a linear global model. Here I'm plotting just the voxels that have a little bit of CSF. So all of these voxels here have less than 5% CSF. And this means that the sum, almost the sum of the white and gray matter fractions equal 1. So I can kind of plot them as a function of the white matter fraction unambiguously. And you can see, again, you should imagine having a sort of a line going through these, the linear regression line going through these, and you can see that it sort of tilts starting up here and tilts down as you go through the data. So the more white matter fraction you have, the lower the signal is. Finally, this histogram over here gives you the residual, meaning the difference in each of the voxels, MRSI voxels, between the global linear value and the actual measured value in each voxel. So the fitted minus the experimental NAA values. And this should be, in a reasonable data set, this should be normally or approximately normally distributed. So it's a good sanity check if you see something that is not normal, that the linear regression model probably doesn't fit your data. This could be for many different reasons. Maybe you have some sort of experimental bias in your data set. Maybe you have a small number of voxels, so they're not normally, so you can't really see the normal distribution, might look weird, and maybe some other reasons I can't really think of at the moment. So this concludes going through this example, and you can see that really it's neatly divided into load your data, first part, then calculate the white, gray, and CSF fractions in each of the MRSI voxels, and then run the linear regression, which is really just one command. And that's it. That's all you need to do to get global white matter and gray matter fractions.